Number 1 gives us the graph of quadratic function f. It says Andre uses the expression x minus 5 squared plus 7 to define f, and Noah uses the expression x plus 5 squared minus 7 to define f. Do you agree with either of them? Explain your reasoning. So we can see that these are in vertex form. So let's take a look at what we would get if we plug this vertex into vertex form. So remember that vertex form is x minus the x coordinate of the vertex and then plus the y coordinate of the vertex. So the x coordinate we generally call h, and then the y coordinate we call k from our vertex. So our k is -7 and our h is 5. So we are going to plug in the x value in this place. So our x value from our vertex is 5. So this will say x minus 5. And then we're going to plug our y value in for this k position. And our y value is -7. So if we just kind of clean this up, because usually we, don't write it as plus a -7. Whoops. So this is going to say x minus 5 squared for this first part. And then instead of saying plus -7, we could just say -7. And so that means that we don't agree with either Andre or Noah, because Andre's should have a -7 right here, and Noah's should have a -5 inside of here. So neither one. Number 2, here are the graphs of y equals x squared, y equals x squared minus 5, and y equals x plus 2 squared minus 8. How do the 3 graphs compare? So they're all really similar. They're just moved around in different areas of the graph, right? So they're the same shape, but in different positions. So then it says, how did the -5 affect the graph for x squared minus 5? So what does this -5 do? And this -5 just moves the graph down. So it moves the x squared graph down 5. Which you can say it like that, or you could say it changes the vertex. The vertex moves from 0, 0. To 0, -5. Just moves it down 5. And then how do the +2 and the -8 impact the graph here? So the +2 actually moves the graph to the left, because this would have been x minus a -2. So our transformation is going to be moving it to the left 2 units. And then that -8 is like a plus -8 out here, right? So that k value is -8. So that's going to move it down 8 units. And again, this would mean that we're moving the vertex from 0, 0 to -2, -8. Number 3, which equation represents the graph of x squared plus 2x minus 3 if we move it 3 units to the left? So in this one, you can kind of take a look at these different things. But if we think about the vertex form, right? So if we think about having x squared, and then we think about writing that as x minus h plus k, remember that this is the movement that moves us left or right, going inside of or touching this x value. So the k is going to move it up or down, so we're not worried so much about that. But what we want is to bring this 3 units to the left on the inside. And So 3 units to the left would mean that this h value is going to be a -3. So we would have x minus -3 in here. And that's going to look like x plus 3 because minus a minus is plus. So everywhere we see an x, this needs to happen. Okay, so everywhere we see an x in our original equation, it needs to switch to the x plus 3. And so let me go like this. So this needs to change to this. Everywhere we see an x, okay, now it needs to say x plus 3 instead. So not just here, that would also have had to happen here. Okay, and now we see it in these two places, but then we lost that -3 in this one. So D has the x plus 3 in place of the x's, and it has the rest of the function staying the same. So D is going to be the one that will move it just 3 units to the left. Select all equations with a graph whose vertex has both a positive x and a y coordinate. So your vertex, okay, needs to be a positive x and a positive y. So for part A, our vertex is 0, 0. Well, 0 is not positive, so that one's out. B has an x coordinate of 1 with a plus 0 out here, so our y coordinate is 0, and 0 is not positive. C, the x coordinate of our vertex is 3, because remember, it's the opposite of what's in here. And then the y coordinate is that plus 2. Both of those are positive, so that one's good. D has positive 4 for the x, but -5 for the y, so that's not going to both be positive. E, this inner part, the opposite of positive 2 is -2. So that one fails right away because the x coordinate is negative. F, we've got the opposite of -4 for the x coordinate. So that's 4. And then 3 for the y coordinate. Both of those are positive. And then G has the opposite of 3 for our x coordinate. And then 1 for our y coordinate. And both of those are positive. Number 5, the height in feet of a soccer ball is modeled by this equation, where t is the time measured, where the time t is measured in seconds after it was kicked. So how far above the ground was the ball when it was kicked? So this is the initial height of the ball. So when it's being kicked. So this is when our t equals 0. So if we plug in 0 for all the t's, 50 times 0 would be 0. -16 times 0 squared would be 0. So our initial height is just going to be 2 feet. So at the time that this ball was kicked, it was 2 feet off the ground. Then the second part, B, asks us what's the initial upward velocity, and that's the number in front of our t. So in this case, it's 50. And then our measurement is feet per second. And then part C says, why is the coefficient of the squared term negative? And that's because it's the effect of gravity. And so gravity is going to pull this ball back down towards the earth. So this part would be kind of like, you're starting at 2 and then your initial velocity is 50 feet per second. So if there was no gravity, it would just keep going at that rate up the whole time. And then we've got gravity pulling against it. So it's going to start going like that, but then it's going to start falling back down. So gravity is pulling against it. Number 6, what is the vertex of the graph of this function? So we want the opposite of this x value. So this says x minus 3. So 3 is going to be our x coordinate. And then the number outside here is our y coordinate. So 3, 6 is our vertex. Then it says identify the y-intercept and one of the other points. So the y-intercept, remember, is when x equals 0. So we can just plug in x equals 0 into this function to figure out the y-intercept. So we would do 0 minus 3 squared plus 6. So we have negative and then negative 3 squared plus 6. So that negative 3 squared is 9. So we have negative and then 9 plus 6. So we get negative 3. So the y-intercept here is we plugged in 0 and we got back negative 3. So 0, negative 3 is our y-intercept. Remember that our vertex was at 3, negative 6. So then remember that a parabola is symmetric around the vertex. So that means if we know that there's a point here, we have to have one an equal distance away from the vertex at the same height. So this is over 1, 2, 3, up 1.5 boxes. So over 1, 2, 3, up 1.5 boxes would be another point. That's the point 6, negative 3. Okay, since we're counting by 2's on the y, so this would be at 6, negative 1, negative 2, negative 3. So that's another point that we can plot. And then we can connect the branches here for our sketch. You could also plug in any value you wanted. So you could plug in 1, 2, 5, 6, whatever you want into this graph and get another point. But the symmetric one is nice because you don't have to do much calculating. You just know there's going to be another one the same distance away. Number 7, at 6 a.m., Lynn began hiking. At noon, she had hiked 12 miles. At 4, Lynn finished the hike with a total trip of 26 miles. Which time interval was Lynn hiking faster, and how do you know? So she started here at 6 a.m., then she hiked until noon, then she hiked until 4 p.m. So from 6 a.m. to noon, she had hiked 12 miles. And then from noon to 4, she ended at 26. So that means she hiked another 14 miles so that her total trip was 26. So in order to figure out how fast you're hiking or how much you're going per hour, right? 6 a.m. to noon, remember noon is 12. So 6 to 12 is 6 hours. And noon to 4 is 4 hours. So she hiked more in the second half in less time. So she's obviously traveling faster from noon to 4. You can also calculate it. So this one, she went 12 miles in 6 hours. So that gives us 2 miles per hour that she's hiking for her speed. And here we're 14 miles in 4 hours. So 14 divided by 4 gives us what, 3.5 miles per hour. So that's faster. Okay, so the noon to 4 is when she was hiking faster. Number 8, Kieran bought a smoothie every day for a week. Smoothies cost $3 each. The amount of money he spends in dollars is a function of the days buying smoothies. Sketch a graph of this function. Be sure to label your axes. So we know each day. So I'm going to just put, we're doing this for 7 days, right? Because it's for a week. So we'll do 7 days. And then the cost of the smoothie is $3. So I know each day he spent $3. Then, so I'm going to count like 7 times 3 is 21. So let me just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm just going to count by 2's here. So 2, 4, 6, 8, this would be $10. And then 12, 14, 16, 18, $20. So after one day, he spent $3 because he bought one smoothie. Then he was at $6 after the second day. Then he's at $9 after the third, $12 after the fourth, spends another $3 to be at 15, another $3 to be at 18, and then another $3 to be at 21. So here's the amount of money that he had spent each time. So really the domain here, he's buying a smoothie every day. So your domain is really just going to be those exact numbers, 1, 2, 3, 4, 5, 6, and 7. Not partial days, because he's not going to, we're not going to calculate it at the end of 1.5 days. He buys one on day 1, another on day 2, another on day 3. So we don't really have partial numbers here. And then same for the range. He's spending $3, $6, $9, $12, 15, 18, and 21. He's not spending $10 because they're $3 each. He's not spending $14 or $20. He's spending multiples of 3 between 3 and 21. Number 9, a deposit of $500 has been made in an interest-bearing account. No withdrawals or other deposits aside from interest are made for 5 years. Write an expression to represent the account balance for each of the following situations. So we know that in each of these we have $500 being deposited. So then we have the 100% plus we're going to deal with the interest rate. And then this is going to be taken for 5 years. So I'm just going to outline each of these and then we'll calculate it, or we'll add in the interest rate in a second here. So this is kind of the outline that we know for every single one of these. So now the interest rate here is 6.5%, okay? And each time it's 6.5%. And as a decimal, that's 0.065. So we know that this is going to be the same in each problem, or like start the same. So now what happens is then this is going to be calculating differently. Here we're calculating it every month. So we want to be looking at this. This is for 5 years. So how many months are there each year? And we're going to divide the interest rate up by that amount. So it's going to pay out part of this interest each month. So we're going to pay this out 12 times. And that means that we're going to have to calculate this out 5 times 12 as well. So we're going to divide the interest down for each month. And then we're going to multiply up here that we're paying it out 12 times in every 5 years. So in part B, the interest is being calculated every 2 months. Well, that means that this is going to be happening 6 times in the year because there's 12 months in a year. So every 2 months we're calculating out or giving out the interest. So then that's going to multiply this to give us 6 times 5. So 6 times per 5 years. In part C, it's calculated quarterly. This is 4 times a year. So we're going to divide the interest into 4 equal chunks, and then we're going to pay it out 4 times every year for 5 years. Semi-annually means twice a year. Okay, so 2 times a year. So we'll split this interest rate up into 2 chunks, and then we'll pay it out 2 times every year for those 5 years. Number 10, function h is defined by h of x equals 5x plus 7, and k is defined as k of x equals 1.005 to the x. Complete the table of values for h of x and k of x. When necessary, round to 2 decimal places. So if we plug into here, we'll be doing 5 times 1, which is 5, plus 7 is 12. 5 times 10 is 50, plus 7 is 57. 50 times 5 is 250, plus 7 is 257. 5 times 100 is 500, plus 7 is 507. Then for k of x, you'll want to just type this into your calculator. So 1.005 to the 1 is 1.005, but we'll round to 2 decimal places like it said. So that'll round that up, okay, because this is 5 or higher, so it'll round up. If we bring it to the 10th power, we get 1.051, so we'll round to 1.05. If we bring it to the 50th power, we get 1.28. And if we bring it to the 100th power, we get 1.65. So then it says, which function do you think eventually grows faster? And so that's going to be k of x because it's exponential growth. So the exponential growth is eventually going to overtake the linear. Now this one has a really, really low growth factor, right? 1.005, and we can see it's growing really slowly. After 100 plugging in, it's still very far apart, 500 versus 1.6. So when they say eventually, they mean eventually. This one's going to take a while. So if we use graphing technology to verify this, okay, it took, okay, until like 1800. So plugging in 1829, because 1828.89 is when they're equal. So it's going to happen. It won't overtake, this exponential won't overtake it until like 1829. It'll finally be higher than the 5x plus 7 was. But it does eventually get there, right? And then the output is at over 9,000.